and circular permutations. Marketing professionals sometimes investigate the number of permutations and arrangements of letters to create company or product names. For example, the company Jataco was derived from the first initials of the owners Alan, Anthony, John, and Thomas. Suppose 5 high school students have developed a website to help younger students better understand first-year algebra. They decide to use the initials of their first name to create the title of their website. The initials are E, L, O, B, and O. How many different 5-letter words could be created with these letters? If we use the permutation formula, we come up with 5 factorial, which is 120 different names. Here are some of them, but we're going to color the 2 O's to differentiate them. So a red O and a blue O. So notice that since we have 2 O's, we will have repetitions unless we differentiate the O's by color. Right? For instance, ELOOB is the same for both O's if the O's are not colored. And so we could also say, the names that these O's stand for. So we could have Owen and Olivia. And so the red O is Owen and the blue O is Olivia. So Olivia and then Owen, or Owen and then Olivia. So for permutations with repetitions, we want to eliminate those repetitions. And so we're going to divide by the number of repetitions, factorial. So here, because we have the O's being repeated, right, we're going to end up dividing by 2 because we have 2 of each. We have a red O, blue O, and then a blue O, red O for every permutation. And so we're going to end up dividing by 2. But if there were 3 of them, there would be 3 factorial, right? So if we had a red O, a blue O, and a green O, there would be 3 factorial ways to arrange them, right? You could have red, blue, green. You could have red, green, blue. You could have blue, red, green. You could have blue, green, red. And you could have green, red, blue, and green, blue, red. So you have 3 factorial, which is 6. So you get 6 times as many things as there should be, because all of these are the same if we don't color them. So that gets us this formula. Number of permutations of n objects of which p are alike and q are alike is n factorial over p factorial q factorial. And you can have as many repetitions in the denominator as you have. We're just only showing 2 because otherwise that'd be a lot. But you can, as many repetitions as you have. So using this formula, there's only 5 factorial over 2 factorial because we have 2 O's, and so that gets us 60 permutations. How many 8-letter patterns can be formed from the letters of the word parabola? Right? So 8, using our permutation formula, that would be 8 factorial. But we have 3 A's. I want that to be 3. We have 3 A's. So that's going to be 8 factorial over 3 factorial. Nothing else repeats, so we don't need to worry about that. And if you wanted to simplify this, 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, you could cancel out the 3 2 1s and get 20, 120, whatever, times 8 times 7. 6,720. Right? Similarly, how many 11 letter patterns can be formed from the letters of the word Mississippi? So 11 factorial, because there's 11 letters. But then what do we have the duplicates? We have 4 I's. So that's a 4 factorial. We've got, or 4 S's, I mean. We have also 4 I's. So that's another 4 factorial. And then we have 2 P's, so that's a 2 factorial. So it's going to be 11 factorial over 4 factorial, 4 factorial, 2 factorial. If you're doing this in your calculator, you're going to need parentheses around that denominator. And so if you do 11 factorial over 4 factorial, 4 factorial, 2 factorial, you get 34,650, which is still a lot. But compared to just 11 factorial, which is going to be really huge, 39,916,800. So much fewer, many fewer patterns when we eliminate those repetitions. All right, so far we've been studying objects that are arranged in a line. Consider the problem of making distinct arrangements of 6 children riding on a merry-go-round at a playground. So now we're in a circle, right? So we could have 1, 2, 3, 4, 5, 6, or we could have 6, 1, 2, 3, 4, 5, or 5, 6, 1, 2, 3, 4, etc. When objects are arranged in a circle, some of the arrangements are alike. In the situation previously, these similar arrangements fall in groups of 6, each of which can be found by rotating the circle 1/6 of a revolution. Thus, the number of distinct arrangements around the circular merry-go-round is 1/6 of the total number of arrangements if the children stood in a line. So we have 6 factorial divided by 6, which is, right, if we, 3 times 2 times 1 over 6, we would cancel those 6's, and that's 5 factorial. So that gets us this formula. If n objects are arranged in a circle and there are then there are n factorial over n, or n minus 1 factorial, permutations of the n objects around the circle. If the circular object looks the same when it's turned over, such as a plain keyring, then the number of permutations must be divided by 2. You cannot turn over a merry-go-round with children on it, so that doesn't apply. If n objects are arranged relative to a fixed point, then there are n factorial permutations. Circular arrangements with fixed points of reference are treated as linear permutations. At the family-friendly restaurant, 9 bowls of food are placed on a circular revolving tray in the center of the table. You can serve yourself from each of the bowls. Is the arrangement of the bowls on the tray a linear or circular permutation? Obviously it's circular because it's a circular tray, and there's no point of reference. So how many ways can the bowls be arranged? There are 9 bowls, so 9 factorial over 9, which is 8 factorial, which is 40,320. Seven people are to be seated at a round table where one person is seated next to a window. This one is going to be a linear permutation because the window is a fixed point. So here's our window, and we have, 7 people? So A, B, C, D, E, F, and G right? Here's one arrangement of 7 people where G is next to the window. If I do this, D, E, F, G, now A is next to the window. The order doesn't really change because A is still between B and G is still between A and F, and so on. But being next to the window is different. So this gets treated like a linear permutation. And so it's going to be 7 factorial, which is 5,040. And that's the end of 13.2. Come back next time for 13.3, probability and odds.